In this video, I'm going to walk you through 3 different ways of saving data so that we can refer to it later. We're going to look at how to create a reference waveform and place it on the screen so we can compare it to other real-time measurements. I'm going to show you how we can take whatever is on that front screen and save it as an image to a thumb drive, and then I'm going to show you how we can take the actual measured results, the voltage versus time data, and save it to a CSV file so that we can bring it into other tools like a simulation program so we can immediately compare the measured results with the simulated results. But before we get into saving the data, I'm going to walk you through again the important setup features that we're going to want to always follow with the scope. It's sometimes difficult to see the details on the front screen, and so I've got the output, the VGA output of the scope, I'm bringing it in here on the screen, so now we can use this to see all the data while I manipulate the buttons over on the front. If you're coming to the scope and someone else has used the scope, you have no idea what some of the special settings might be. And so the first button that you should always push when you come to the scope for the first time is Default Setup. And that will bring all the different features in the scope, or most of them, to a known starting place. So I'm going to push Default Setup, and it's going to go and it's going to readjust things, and there the default setup is loaded. Second thing you want to do is check the probe attenuation. In this particular set of measurements we're doing, I have a simple coax cable connected to the scope going into a function generator. And then the details of the function generator we're going to cover in another video. In this particular case, it's just a simple signal source. But the key feature is the cable is a 1x cable. There's no attenuation in it. It is not a 10x probe. And I want to be able to display on the front of the screen the actual voltage coming into the scope through that coax cable. This particular scope, channel 1, you can see here, is set for 10x. Which is great if I had a 10x probe attached, but I don't. And so what I want to do is change that. And we can adjust the scales and the screen settings in a number of ways. One way is we can literally touch that attenuation value, brings up a contextual screen, and we can change it over here and make it 1x. That's one way of doing it. Another way is we can push the channel 1 button to select that channel, and you notice we get contextual menu coming up at the bottom. And if we scroll all the way around, up there's the probe, and now we have the option of, oh, what setting do we want? We can touch that screen. It says ratio. We say, okay, let's change the ratio setting, and we get that same screen. And we can type in 10 if it's a 10:1 probe, or we can type in the 1 if it is, as we have here, the coax. So now the scope is set. The next thing that we're going to adjust is the scales, the vertical and the horizontal scales. Now when we pushed Default Setup, it gave us nice whole numbers for those scales, with the center at 0 for voltage and the center of the screen where that caret is. That's where we're adjusting the t equals 0. That's where we're triggering the signal at, also at 0. For me personally, I think it's really important to have whole numbers on the axes. That way I can immediately read what the values are off the screen. Now, if it was offset like this, for example, and I'm just arbitrarily moving the position and the vertical and the horizontal, I have the scales listed on the front of the screen, but oh my gosh, it is so hard for me to read. Well, what's the value of the signal? What's the average? What's the peak-to-peak value of it? What's the time interval associated with it? I have to do a lot of calculation in my head, and those are hard things to do with those oddball cockeyed numbers. Remember one of the important engineer's mottos: computers work for us, we don't work for computers. Why make your life so much harder to read the values off the front screen? And remember, before you do any built-in measurements or use the cursor, always set up the scope in order to read a measurement with your Mark I eyeball off the front screen. That way you know what to expect from a measurement, and you can compare the value of what you've measured with your eyeball with what the instrument tells you. If you can't read that value accurately with your eye, how do you expect the scope to be able to do it? So one of the important steps after the scope is set up is to adjust the scales. And for me personally, I like to see 0 volts in the middle if it's appropriate. And so I can move the vertical control until somewhere I find the 0, or the trick is you push that vertical adjust button in, automatically centers it. And look, now we have nice whole numbers on the vertical scale, and when I expand it, oh wow, look. Now I've got nice whole numbers when I'm expanding it. Same thing with the horizontal. I can move it around until that caret's in the middle there, or I can push the horizontal button in, automatically centered. Wow, look at that. Now I've got my vertical scale is 50 millivolts a division. My horizontal scale is 100 microseconds. Now, I really want to get an idea of what that period is, so I'm going to add a couple of more cycles in there. And now at a glance, it's effortless for me to extract a few of the important parameters of this waveform. I can get the peak-to-peak value because look, that's 100 millivolts high, minus 100 millivolts, plus and minus 100 millivolts are the values, which is 200 millivolts peak-to-peak, which is the peak-to-peak value for this sine wave. The second important parameter is the period, and look, I can read that right off the front screen. Here's the 0 crossing, here's another one, this is 1 period. And see, that's 2 divisions. I've got the values for those parameters. Okay, now the scope is set up. I can read the important features of the waveform that I care about right from the front screen. And now I'm going to show you the first way of saving this data, and that is using a reference waveform. To access that feature of reference waveforms, we're going to come over here in this section here that's the where you see the math functions and some special functions, and I'm going to push reference. And this particular scope has 4 different registers in which we can save reference waveforms. They're labeled as, very cleverly, R1, 2, 3, 4. We can only save one at a time, but we can save 4 different ones. And as soon as we push the reference button, it's highlighted over here, you can see that we've got a contextual menu down below. And we can decide which of those 4 registers do we want to display. Let's display register R1. And if we want to display one of the others, we could, again, click the button to open up our options. Let's do register 1. Now it's going to be displayed. Whatever I have stored in there is what is going to appear on the screen. And now, in order to save a waveform in that register, you'll notice we have, again, the contextual options. I want to save it from channel 1. I could change the location. I want to save it from channel 1. And I'm ready to save it in there. And what are we going to get? We're going to get these scales, time and voltage scales, and we're going to get that waveform that's currently displayed in channel 1. So I say save to register R1. And there we go. And you can see that orange waveform. Now, we have 2 waveforms that we're displaying on the screen, the reference waveform and the real-time waveform. I'm going to shift the position of the real-time waveform up a little bit. So there we go. The orange is the reference waveform. And of course, if I want to turn it off, we've already got the reference highlighted. We've got the contextual menu here. I can come in here. I can turn off that waveform. And if any time I want to, it's saved in memory, and I can turn it on again. In addition, I can change the scale, and the 2 knobs up here are to adjust the scale. So I can adjust the vertical offset position of the waveform. I can change the vertical height of that waveform as well. So I'm changing the scale with the 2 knobs. I can also, again, so many of the functions, we have 2 options. I can also come over here, push that in, and now I can manually change the vertical scale, and I can also change the offset. Whenever we have a waveform displayed on the screen for this particular scope, the horizontal axis is tied to every one. They all have exactly the same time base. And so when I change the time base, you'll notice I'm changing the time base for both waveforms. And so I can change the time per division. I can move the time t equals 0 around, and you'll notice we're changing both the real time and the saved waveform. And I center it again, and I center it again. So again, keep in mind though that the vertical scale can be adjusted independently of the two waveforms, the reference and the real time. Real time is always controlled by the channel, and the reference is controlled by the knobs over here. So let's move it back up. There we go. And we can compare the reference waveform with any other waveform. So for example, I'm looking at the real-time waveform in channel 1. I'm going to change the frequency a little bit in the source. So I'm changing the source waveform, and you can see, oh yeah, they're not lining up anymore. And there's no amount of motion, vertical, that is going to line them up because, hey, they're different frequencies. First way of saving data is with the reference waveform. So I'm going to keep that reference waveform on. And you'll notice also that the last button that I touched, in this case the reference waveform, the vertical control, look at what's happening on the screen over here, that we're displaying the scale of the scope for the reference waveform. And that can be different from the vertical scale for the real-time measurement. If I want to display the vertical scale for the real-time measurement, all I have to do is make an adjustment on anything related to channel 1, and you'll notice that scale displayed on the screen automatically changed. And I'm going to move it back to the center here. Everything that we see on the screen at this instant, we can save as a bitmapped image of the screen. And the way we do that is we're going to save it to as a bitmap image onto a thumb drive. So first step is I'm going to add a thumb drive to the USB ports at the bottom. I've got my thumb drive inserted, and now we're going to come along and we're going to come to the buttons over here under File. We're going to push Save Recall. And again, when we do that, we get a contextual menu on the bottom. I'm going to click the Save option, and we have a number of options for the Save option. In this particular case, I'm going to use a 24-bit bitmapped image. This is going to come out as a color image of the front screen. The 8-bit is going to come out as a black and white. You can save it as bitmap or a PNG. So we can do a PNG file as well. Once we've identified what kind of format that we want, we're going to say yes, we want to save it to the USB, and here's where it's going to be located. And now we can adjust the file name. If you want to, there's a default name that comes up. We have the increment button selected, and that means it's going to automatically increment the number that's assigned to that image. I find that really convenient. Or if you want to take the time, you can click that, open up a keyboard, and you can type in a value. I find it, awkward keyboard on the front interface. I'm happy just using an incremental number, and then I can take that waveform immediately out of the scope. It's on the thumb drive, put it in my computer, and then I can relabel that image immediately to make it easier. So we've got the file name set up, and literally all we do is say, okay, we're ready, save it. It's going to take a screen image of everything we see on the screen. So make sure before you save it that the scales are nice scales. Why would you want to have something that looks like this or like this, so that when you save this data, it's really hard to read what is the scale. Make it easier. Remember, the reason we're saving a waveform is because we want to illustrate a measurement. We want to show it to somebody or recall it later. And why make it hard to read the values off the front screen? So always adjust the scale values so they're nice whole numbers, so at a glance you can tell exactly what the values of that waveform are on the screen. Now we're ready to save. Press the Save button. It's saving it. This is scope image 8, and we're done. Just to test that, let's take that thumb drive, let's put it in the scope, and let's look at that image that we saved in the scope. Here it is. We're going to double click to open it, and look, there is that image that we saved. It's got those nice scales. I can read with the scales per division. I can read the 50 millivolts per division here. I can read up here, yep, it's 500 microseconds per division. Easy to read. And I can come over here and look, I can read the vertical scale for the reference waveform as well. All that data is there and preserved. So first way of saving the data is a reference waveform. Second way is a screen image. Now comes the third way. And the third way is we're going to save the actual data itself in a CSV file. So we've got our waveform up here in channel 1, and I want to save the CSV file. So again, we're going to push the save and recall if we haven't already. We're going to push the save in order to now bring up the contextual menu, and we're going to select the format that we want now is CSV. So we say save CSV. It's going to save to the USB drive. Again, file name wise, it's okay. Same file. It's an incremental file number, and we say save. And now it's taking that measurement from channel 1 and it is saving it as voltage versus time. Let's take a look at that data. Here is the scope 9 waveform in CSV, and if I open it with something like Notepad++, here is all that data. Now, when I pushed save, it's going to take all the data that's on the front screen. In this case, I had two waveforms. I had the channel 1 data and I had the reference data, and it's going to save both of those. Remember, every waveform that I have on the front screen always has the same time base. So the first column over here is the time in seconds. The second column is the voltage in volts for channel 1, and the third column is the voltage for the reference waveform. And so I have all this data. There are 2,000 points here all the way to the bottom, and I have this available that I can plot. I can literally copy and paste this into Excel, for example. I can copy and paste it into a circuit simulator like Circuit Labs or like ADS. And now I can bring that measured data into my simulation environment and compare the actual measurement with the simulation. So those are the three ways that we can save data. Depending on our application, we're going to use one of those three methods.